Hello, so today we are going to talk about an interesting also algorithm concept, which is Hamming distance. So Hamming distance is, I think, a good application of XOR, XOR binary operator, which comes up often both in late code, in interviews, and in comparative programming. And also Hamming distance concept also itself comes up. So it's both are good to know. So yeah, that's why I thought we could cover this today. So what is the Hamming distance basically? So the Hamming distance between A and B is just the number of positions between A and B that differ, right? And sometimes it may mean not binary, but most of the time it's for binary representations. So let's say, for example, if I'm looking for the Hamming distance between maybe these two binary numbers, so 1101 and 11001. So where do they differ? This 0 and 1 are the same, in the same position. However, with these three, only this one is in the same position, but these two are different. Only these ones in the same position have the same value, but this one and this one differ, right? Which means that we need, this is equal to 2, so the distance is 2. Okay? Okay, so let's take a look at this example. So suppose you get like n-bit strings, each of length k, and you want to calculate the Hamming distance between them. So for example, if we take these two here, this one and this one, what's the difference? So this difference is only here, right? So that's 1, and there is another difference here. So 2 here for this one, right? And if we take a look at this other example, these two differ, so 2 here, and then this one differs, so 3, right? So if you have like just two strings with binary that you want to count the number of differences, how would you do it? The easiest way is definitely to do brute force, right? So let's say we have maybe a function that want to calculate for A and B the Hamming distance, right? So we can just have our count equal to 0, right? And then we just go through, we know that the length is k, so we go through the range of k, and we just check if A at that position is different than B, then we increase our count and we return the count at the end, right? So pretty straightforward. So this solution would work, but we can actually optimize it because this is O of k, right? We can optimize it to even O of 1 using XOR. Let's see how. So how do we do that? So we can actually, if k is smaller than 32, which means these strings will fit in an integer representation, we can just convert these strings into integer, and using bit operation, we can calculate it in O of 1. Why is that? Because XOR, for XOR of A and B, what will it do? So let's take, for example, here. So XOR will, if the bits representations at one position differ, it will set 1. If they are the same, it will set 0, right? So if we apply XOR, then places that have 1 in them means that at that position A and B have different values. So all we need to do is just count the number of ones, and we'll get the exact Hamming distance we are looking for. So let me show what that will look like in the second example. So if we have 0, 1, 1, 0, 1, and here 0, 1, 1, 1, 1, right? So what will XOR do here? If two are different, so like 1, 0, XOR will return 1. If they are different like this, it will return 1. But if they are the same, it will return 0, right? If they are the same, regardless what the value is, it will return 0. And that's exactly what we want with the Hamming distance, which is when they are different, we want to increase the count. And so here, this will tell us, okay, these are different, this is 1, these are different, this is 1, the same here, 0, the same here, 0, these are different, so 1, okay? And just we count the number of ones because those means that the positions have different values. And so if we count the number of binary ones here, that will be 3, okay? And so to do that, we can just, instead of doing this loop here for the Hamming distance, we can just define a function like this. And we convert our strings into an integer representation. So int A, int B representation here. This is not like the correct syntax, it's just pseudocode here, by the way. And so what we can do is just get A XOR B, and then we want to count the number of ones. In different languages, you can do it differently. For example, in C++, you could do built-in pop count. In Python, you could do convert to binary and then just count the number of ones. You could also do it in binary, like doing a loop with 32 and then just checking how many bits are set here. Yeah, and that's pretty much it here. And this here would be O of 32, which is constant, right? Because we will count, we will do a traversal to count how many ones are set. Yeah, so yeah, this is a nice applications of XOR operator. Yeah. One thing I want to mention here is for languages like C++, built-in population count may be faster, but for Python, this here is O of log n, just the bin function itself. Because it will divide the number log base 2, because it will keep dividing the number to get the bit position. So this is just something to know and particular to Python's implementation, but the general idea stands that the XOR would be faster than doing a for loop. Yeah. Yeah, so that's pretty much it for the topic today. Thanks for watching and see you on the next one. Bye.